Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at a different concept, and this is the concept of Heisenberg's uncertainty principle. Now, from classical physics, the laws that are already in existence can assist us to pinpoint where a particular particle is. But since the development of the concept of a wave-particle duality, then the concept of a wave brought in a challenge is that we cannot be able to describe the momentum and the position of a particle at the same time. So this gives rise to Heisenberg's uncertainty principle. And we're going to look using the sample question on the board on how we can be able to tackle a question that regards to that specific principle. So without further ado, thank you and welcome. So in that case, our topic for discussion for today is going to be Heisenberg uncertainty principle. And this one, of course, is a concept that was developed after the concept of a wave-particle duality was developed. In that, Heisenberg and Bohr, of course, come to a conclusion that there must always be uncertainties in measurement when you are trying to describe the position and the momentum of a particle at the same time. And therefore, this is because the precision to establish the behavior of particles, which are of course like subatomic particles, requires us that these two variables, of course, must be measured. Therefore, as we have said that the laws of classical physics, in the laws of classical physics, we are able to establish, of course, the momentum, and we can be able to describe the position of a particle. But since the concept of wave-particle duality gives us a sense that particles can behave as waves, it is difficult for us to pinpoint or maybe try to give a particular location in space whereby we can find a wave. Therefore, we're going to give a specific concept pertaining to uncertainty. And this one is to be able to locate maybe a particle by combining several waves of different wavelengths. And this is going to give us the concept of a wave packet. And this basically gives us a probability of finding a particle in that particular space. So therefore, to try to illustrate this concept of a wave packet, we're going to use the concept of normal waves that we have learned. And as we can be able to illustrate, or maybe I'm just going to use this. We can have waves of different wavelengths, maybe like that. Now, in this case, in trying to find these different particles, the particles which are maybe in space, we can sum up those waves in order to find the average through the proposition of different waves, which will yield for us an average wave that is used to localize what we have referred to as a wave packet. Therefore, in this case, we're going to have a wave that is going to have a of that characteristic in nature, whereby we're going to find that we can be able to find a higher probability at this particular point, or the average. So therefore, in trying to describe the de Broglie's wavelength, we're therefore going to use that average for the lambda and find that it will be given as h over the change in that particular momentum. So in this case, this is trying to give us a position of a particle. In that, as we said, for this particular case, we can be able to describe momentum of that wave particle using the de Broglie's equation. Now, there's this concept that the greater the number of course of the waves that we have illustrated on the board, there's the greater the probability, of course, of trying to find that particular particle in space. Now, because these different waves have different values for momentum, and therefore there is going to be what we call uncertainties. This is uncertainties. uncertainties. Sometimes in physics we refer to this one as errors, or maybe where the deviation from the true value. So therefore we're going to have uncertainties in the resulting momentum. That is why we have indicated this one as a particular change. So this gave concept to the, of course, the equation of Heisenberg's uncertainty principle. And therefore this equation is going to describe the product of uncertainties in position and uncertainty in momentum. And it is given by these values, whereby uncertainty in position and uncertainty in momentum is going to be given as h over 4 pi. So from the way, or from our previous discussions, those are the constants for h and pi. So therefore we are just going to use that kind of a concept in trying to find the uncertainty that we are being asked for in our question there. So the question states that a 12 electron volt electron can be shown to have a speed of 2.05 times 10 raised to 6 meters per second, assuming that the precision, that's uncertainty of this value, is 1.5%. With what precision can we simultaneously measure the position of the electron? So therefore in this case we are being asked to find the uncertainty in position of this specific electron. Therefore first we are going to find what we call the uncertainty, or maybe the change, the speed which has been described there. So we have been told that an electron can be shown to have a speed of this one, assuming that the precision uncertainty of this value. So there's an uncertainty of this value for speed, which is of course that percentage is the same as 0.015 times that speed, 2.05 times 10 negative 6 meters per second. So then whenever we're trying to measure something like efficiency, so we just use a percentage. For this case of uncertainty, therefore we're going to use that particular value in order to find the specific speed that is being referred to. So in this case it's going to be 3.1. This is 3.1 times 10 raised to 4 meters per second. So including that aspect of uncertainty, this is the speed that we're going to get. But we know that momentum is given that this is the speed. So momentum is given as mv. Therefore the change in momentum, mass being constant for electron, is going to be mass change in speed. And this is the uncertainty in speed that we have already found as a value here. So therefore we're going to do a substitution for us to find the momentum of that particular particle. And we will have, that is a change, or uncertainty in momentum is given as mass. This is an electron, therefore the mass is times 10 negative 31 kgs times this particular value, 3.1 times 10 raised to the power 4. So therefore this is going to be, this is in form of kilograms, and this is in meters per second. So that is for this going to be kilograms meters per second, and that is going to be 2.8 times 10 negative 26 kilograms meters per second. So the uncertainty's momentum is going to be that value, and therefore given from the Einstein's uncertainty principle equation that we have there, we can be able to find uncertainty in position. Just do away with this. So we can find uncertainty in position by giving it as, now this equation will translate to the uncertainty in momentum is equals h over 4 pi. We're trying to make this one the subject of the formula. So for that case, we're going to have this one given as, we just do a substitution for this figure in this, and then this and these are a constant, which of course we know this is h 6.6, I mean 626, then negative 34 joules second. So this case we're going to do a substitution and we'll find it is a 1.885 times 10 negative 9. So this is with the uncertainty in position of that particular particle, which is an electron. So this is the strategy that we are going to use when trying to find out this particular uncertainty, either in momentum or uncertainty in position of this particle, which is trying to describe, of course, the Heisenberg's uncertainty principle. So of course we are going to find much of many other questions which are related to the same, and we're going to tackle them as they require, especially if we are trying to find out whether it is uncertainty that we are required to find on in position etc. So in this case we are going to stop it there for today and try to find out other ways in which we can be able to describe this. But of essence is us to try to confirm that the calculations that we are doing are accurate, so that we do not miss out on finding the accurate figures. So in this case, for the constants that we are using, like the h, the pi, and others, these ones are normally provided, unlike in the one that I've written on the board. These constants will always be provided, and it will be of essence for us to be sticking to the ones that we have been provided with in order for us to be accurate in our maybe evaluation. So that is it for today. Thank you guys. Bye. God bless.